Perché la supernova? Ma mi pare strano, con Luca, se fosse supernova l'avremmo sentito che lo diceva, farà un'altra roba, no, Achille lo conosco bene, ma Michele, ora così i nomi, mi hanno detto che non coppia. Avete sentito ieri che...
Penso che sei registrato, no? Non ancora, no.
Hai sentito che la giornalista di Canale 5 parlava di questa roba del 2009, chiamato Nanni Bignani, ha detto
sì.
Il presidente professore di astrofisica Nanni Bignani,
e invece era Piero Bignani.
No, Giovanni Bignani, che è il giornalista.
No, Luigi Bignani.
Luigi.
No, lei ha chiamato Giovanni
e lui era Luigi.
Ha fatto una gaffa,
una gara, vabbè,
lo sapevo.
ma mi hanno detto invece, parlavo con questo Achille mi fa, sì, come Piotto che ieri ha presentato un dottorando che si chiama, dico Maurizio Pino, e lui l'ha chiamato Pino Daniele. Questo è più complicato. Pino Daniele. E ho detto questo Pino non ne può più perché lo chiamano Pino di nome, no?
Invece Pino è il cognome. Ma è Lorenzo Pino? È Lorenzo Pino?
Potrebbe.
Lo conosco.
Io no.
È uno che aveva fatto la laurea a Milano.
Potrebbe.
E che è qua a Padova a fare
dottorato, capito?
pianeti? È possibile?
Mi ha detto che stiamo dottorando.
Sì.
Io non lo
Nuovo di quest'anno.
Nuovo,
No.
che appunto...
Sì, è il nuovo di quest'anno?
Credo di sì, perché diciamo, mi raccontavano che è stata la
Questa
presentazione, l'ha
presentazione.
presentato come
Fino adesso. Cominciamo?
Quando vuoi tu?
Faccio in due parole di presentazione.
Spero.
Sì.
Quello che ha lavorato con la Michela,
Sì.
c'è? O non c'è? Non è più qua? È qua?
Dovrebbe essere ancora qua. Che io
Sì, ma non
sappia.
c'è qua in sala.
In questo momento non lo vedo. No. In questo momento
No,
non
scusa,
c'è.
avevo una, non so se lo dico, però c'è questo speremapelli nell'articolo, eccetera. Se per caso lo cito, non vorrei citarlo a sproposito.
A sproposito.
Che non so che faccia. È solo per
In
quello.
questo momento non c'è.
Comunque è qua ancora, sì.
Che io sappia.
Lavora qui ancora, anche se la Michela.
Tutti indisciplinati, non fanno schifo. Questo è carissimo. Andiamo? Sì, sono d'accordo. Come facciamo, in inglese o in italiano? No, in inglese.
In inglese.
Sì, ho visto adesso. Mi coprivi. Ok. I think we can start. It's a pleasure to have Anna Wolter here today. We have a long-standing collaboration with Anna, especially on ultra-luminous X-ray sources, and today she's here to talk about this, in particular, ultra-luminous X-ray sources in ring galaxies.
Thank you. It's a pleasure to be here. I've been here already, and I know many of you. The work I'm going to talk about. Cosa devo fare?
Mettiti il microfono più vicino.
Funziona? I've listed here a few of the collaborators. I might have missed someone, so are the main collaborators for this work. And I'm going to speak about especially the ULXs that are in ring galaxies. But first, we want to know what ULXs are. This is a picture of the Antenne galaxy. It's a famous, and it's a beautiful HST picture. The two galaxies are in collision, and you can see from the colors that there is a lot of dust and a lot of new star formation. If you look at the same picture in X-rays, you see that basically the X-rays trace the locus of star formation that you have seen in the optical. Many of these sources are very, very bright, and most of them are ULXs. What are ULXs? They were thought at the beginning, I will go back a little bit later on, to be the missing part of the distribution of black hole masses. As you can see, we know that black holes come in different sizes, and we know stellar black holes, mostly in our galaxy, that have tens of solar masses. And then we know supermassive black holes in the center of galaxies, usually in the million and billion of solar masses. A few of them are just a little bit lower, but there is a huge gap in between these two mass distributions. Why are they important? First of all, because why should they not be there? If there are small ones and large ones, why not intermediate? And then they have important implication for the distribution of masses also in the local universe. In our galaxy, we know masses up to 10 or just a little bit more solar masses. Now, after the gravitational wave measure, we know that there are at least 60 solar masses black hole. They are very important for a cosmology point of view because they could explain the formation of supermassive black hole in the early universe, and they can explain other characteristic of the cosmology, like preheating of the intergalactic medium and other ingredients that you need to make the universe as it is now. The other importance is to make theorists understand how to evolve stars and massive stars and how to make large black hole. As large the black hole we find, and as large the theorist can make the stars and work out some form like the direct collapse to make large black holes. And so the interest for this subject is where to find them, and this is something that we don't know yet exactly how to explain. I went back to the original or old definition of ULXs. They were called IXO at the beginning, like intermediate luminosity X-ray object. IXO recently has been used for the International X-ray Observatory, but this has gone away also because who knows what's the next meaning for the acronym IXO. They are first observed with Einstein, the first telescope that made images in the X-ray sky. And in the review of Fabian et al., you can see that there are 16 sources observed by Einstein with a luminosity larger than 10 to the 39. Why 10 to the 39? This is roughly the Eddington luminosity for a black hole of mass about 10 solar masses. So we know that there are black holes this size in our galaxy. We expect that a larger black hole has a larger Eddington luminosity, and so if we find sources that are of this luminosity, we expect them to have a larger black hole mass to sustain this luminosity. They are variable, and this implies that they are probably point-like, even at the Einstein resolution was not great as what we have now. And they are not in the bulge, the one discovered by Einstein. And so they have the right characteristics to be this intermediate mass black hole. the first review, the first list of this object comes with the advent of Rosat. Rosat makes a large survey of the sky, and Colbert and Tuck published the first catalog of 87 intermediate objects in 54 galaxies. And again, they're compact, they are near the nucleus but not coincident with the nucleus. If you don't have enough resolution, a 10 to the 39, 10 to the 40 ergs per second source might be the nuclear source of the galaxy, of course. And they claim that they cannot be supermassive because a black hole of mass larger than 1 million solar masses via dynamical friction in a Hubble time follows in the center of the galaxy. So if they are not in the center, they cannot be as massive as the supermassive black hole. In 2002, Colbert and Tuck have a list of questions. Do they really have intermediate mass black hole? How did they form? Are they maybe in binary systems? Are they normal stellar mass black holes, but with a beamed X-ray emission, so we don't see the isotropic emission, but just a portion of the luminosity, and so if we multiply by 4 pi, we end up with a larger luminosity than it really is. How they are fueled. Are they perhaps more luminous and more frequent in a galaxy with a high star formation rate, and why? And are maybe different in elliptical galaxies than in other star-forming galaxies, spiral galaxies. We know some of the answer to this question now. For instance, we know that the elliptical galaxy do not contain real ULXs. Most of the X-ray sources that we find in the direction of the elliptical are not in the elliptical, are interlopers, usually background sources. And their luminosity, if they are really associated to the galaxy, they are just above the 10 to the 39 limit. And so they are most probably accretion onto 10, 20 solar masses black hole, as we have some object in our galaxy. So it's not a new population of objects. And so we remove the elliptical galaxy from our perspective. We know that they are linked to star formation. There have been many different papers on the subject. And for instance, if you look at the distribution of the luminosity as a function of a star formation rate, you see that there is a correlation that goes on for many decades. Of course, this is always to be taken with care because the brightest objects are objects in deep surveys, and so in deep survey usually don't have enough resolution to resolve out a possible nuclear source from this luminosity. So this should be the integrated luminosity of all the galaxy, but sometimes you have to take into account that you might have an AGN in the middle. This map is one of the best, I think, demonstration that the ULXs are linked to the star formation. You see that the red dots are the position of the X-ray sources, and you see that they follow mainly the spiral arms where star formation occurs. And Mineo et al. Makes also a nice map of star formation using both GALEX and Spitzer data. And you see that the X-ray sources now are yellow dots, follow roughly the distribution of the position of the high star formation. The connection with metallicity, which has been proposed by many authors, for instance, Luca here and Michela Mappelli, is instead a bit more controversial in the sense that we have some hints that there is a trend with metallicity, but all the results are very low significance. And one of the best results is this difference in very low metal deficient galaxies with respect to the other objects with more intermediate or normal solar metallicity. But this result is a 2.3 sigma result, so it's not there's a hint, but it's not a strong result. Why it is interesting to have low metallicity? Because with in low metallicity you can make a star that keeps most of its mass until the end of its life, and so you can have a larger reservoir of mass to make a larger black hole in the end via direct collapse. And so it all makes sense, but we have to prove it. Now that we are all geared up with intermediate mass black hole, what happens? A couple of years ago, one of these objects is found to be a pulsar. Pulsar is not an intermediate mass black hole. So the first one was found in M82. It was a difficult observation because the center of M82 is very crowded. There are a lot of different X-ray sources. So there was a pulsar. The association with this object was questioned by someone, but after that there are two other objects that have come out recently that also have pulsar. One of them is very difficult to find, and you can see, I don't know if you can see here the spike for the pulsar. If you just look at the data, you don't see it, you don't see any feature above the 3 sigma line. But if you take into account that the period might not be stable and might change during the observation, and you correct for this p dot in looking for the period, then you find a very strong signal of pulsation. And then there is another object, NGC 70C93 P13. This was an object that was already studied for a long time, and some observation had found that the mass of the compact object had to be less than 5 solar masses. But now we find pulsation, and so if it is pulsation, it has to be a neutron star. And so the companion of this binary object, we think that most of the ULXs are binaries, has to be also a neutron star. Of course, with a neutron star, to make this large luminosity, you have to have some specific situation, and one of the ideas is to have a very, very large magnetic field that allows to have accretion arrive very close to the surface of the neutron star. So in the end, what we think now is that ULXs are a mixed bag of sources. There is no clear evidence yet. There are a few cases that are still considered good candidates to be intermediate mass black hole. There is one for which a mass of around 100 solar masses have been sort of measured. Most of them are probably heavy stellar mass black hole, meaning close to 100 solar masses, and possibly with low metallicity, born in low metallicity environments. At least 3 objects are neutron star. We have recently made a paper on the possibility of finding other objects that might be neutron stars and how to discriminate neutron star by binaries, by black hole binaries, just by their X-ray emission, even if we don't find the pulsations. And this is not easy at all. One other possibility is that they are supernovae. Supernovae, there is a specific class of supernovae that are called supernovae 2N or 2P, that which are 2P are the plateau, are supernovae that live in a very rich environment, a very large star that have lost most of its mass via winds. And so when the supernova explodes, it has all this polluted environment. And so the shock wave goes through this very dense area, and it can remain bright above 10 to the 39 for more than 10 years. So some of these objects might be, in fact, supernovae. And so I have a kind of intervallo. No, intervallo, like an intervallo. I had also the, never mind, a break. A break, we cannot avoid to talk about gravitational waves in these days, and so I just want you to show the masses of the detected gravitational events that we have found. These are the LIGO-only events, and you see that we have objects that go up to 60 solar masses. The products of the merger is around 50, 60 solar masses. Most recently, Virgo has also started observing, and so we had another object around the 50 solar masses, and the most recent one announced on Monday instead was a kilonova. Again, we started with very heavy black holes, and now we are going down to find neutron stars that coalesce and make gravitational waves. This is the closest event in gravitational wave that have been studied is around 40 megaparsec distance. So it is an object that is in a galaxy very close to us. So again, we start looking for large objects, and we end up finding neutron stars. So are all ULXs maybe neutron stars? We don't know yet. So where to look for them? And I've started to look in ring galaxies for two main reasons. One, I don't know if you know any ring galaxies. The most famous is the cartwheel. This is a picture, I will show it again, of the famous ring galaxies. The ring galaxies is formed because one galaxy goes almost exactly through the center of a spiral galaxy, and the results of the encounter is a shock wave that sweeps all the area of the galaxy, and it might also involve some gas that is outside the original limits of the spiral galaxies. And so it has the right environment to have a recent star formation, a low metallicity star formation, because the gas outside the galaxy should be primordial, and so is not polluted by heavy elements, and usually with a young age, otherwise we would not see the ring, the star-forming ring anymore. Besides, the ring is a very geometrically defined area, and so seeing sources in that area means that they are most likely associated with the galaxy. So the risk of having interlopers is a lot less. I've looked for the galaxy observed by Chandra, because Chandra has the best X-ray resolution, and so we want to have the best X-ray images. And these are the 7 galaxies observed, ring galaxies observed by Chandra, the cartwheel that is very, very famous, and you can see other rings. Some of the rings are not quite clear, and you might question that, but these are all classified as collisional ring galaxy. Also because they have a companion galaxy at the same redshift, which might be the galaxy that have the bullet galaxy that have made the impact. I will go through them one by one. This is the cartwheel. This is the one that started me working on ULXs and on ring galaxy. This is the X-ray image. This is a composite of the Spitzer, Galax, HST, and Chandra. And you can clearly see that the ring has a recent star formation, while most of the old stars of the galaxy are in the internal ring. And also you can see that these two galaxies are quite different, one from the other. And the disturbed one here was thought at the beginning to be the bullet galaxy, but more recent observation with H1 have found this H1 trail that goes from the cartwheel directly to this galaxy, which is the 4th galaxy of this compact group. And so now this is believed to be the bullet galaxy that went through the center of the cartwheel and made all this star formation episode. They are not oriented in the same way, the two pictures, by the way. This is NGC 92. This is a galaxy that at first was not classified as a ring galaxy because the ring is a bit distorted and not exactly in the plane of the sky. But you can see that the X-ray sources follow exactly the profile of the ring. This is one of the nicest patches of the sky. Beside the ring, you have this galaxy that is thought to be the bullet, a bright star, and just nearby an AGN. So in just less than 1 arcmin, you have everything, all the universe. The pink sources are the X-ray sources. This is the same picture with Galilei added, and this is the X-ray image in which you can beautifully see the ring describing these sources. This is R284. These are two galaxies that look very similar to the antennae that I showed at the beginning. The encounter has made, these are the two galaxies that have been going one next to the other. And this is the central part in which you can see clearly in this HST image the star formation in the center. And this is the image with the contours are the optical and the colored image is the X-ray emission. And you see again that there are very bright X-ray sources. These have all been published, and so I put the papers in which they were published online. But then there are other trees that have not been published yet, and so we are publishing them now in this paper that I'm doing with Antonella and Michela. And this is a galaxy that is also called the Yolk because it looks like an egg, a fried egg. One of the sources, this one here, has been investigated, is the brightest source in the area, has been investigated by Hyde et al. And was found to be a Seyfert galaxy. So it's a background object, it's a Seyfert, and it has nothing to do with this galaxy. This would have not been a problem for us because now we are studying only we are interested mainly in the sources along the ring. So this would have not counted for the ring galaxy. And also the nucleus here is detected as a bright source, while for instance in the cartwheel, which is very, very similar, there is no nuclear X-ray source. Another object is this object is ARP-143. These are the name of the two galaxies. This is the ring. It shows up also in UV. I have not found a very nice image. This is the best I found. And the red are the contours for the X-ray images. And again, the nucleus is present and is quite bright. The last source of the list is ARP-148. This is the most distant one, and it also is not much more distant than the cartwheel, but the cartwheel has been observed for long observation. We asked for 200, 300 kilosecond Chandra observation, while this is only a 30, 40 kilosecond observation with Chandra. So the limiting sensitivity is much higher. So we see just two sources, which are coincident with the ring, but there might be more. And also this galaxy around here, which is most probably the intruder, as you see from the optical image, might have a nucleus, or this might be the integrated emission of the galaxy. It's not clear. And also being so far away, also the Chandra resolution is not enough to see with a small number of count many different details. So we would need to observe it for a longer time. So now we have collected all these 7 sources. We have a lot of sources detected, individual sources detected in the rings, and we can compare them with other categories or other classes to see what these sources are. And we want to construct their luminosity function and compare it with the luminosity function of other classes. And for instance, this is the paper from Grimm et al., 2003. They have constructed the universal luminosity function of high-mass X-ray binaries. So they've taken different galaxies, and they have normalized the galaxy to their star formation rate and found that they all are similar, and they agree, and they present a sort of cutoff, so there are no sources brighter than a few 10 to the 40 X per second. And so they constructed this luminosity function, and we can consider that the ULXs are the high luminosity tail of these high mass X-ray binaries. The hypothesis of having high mass is consistent with both having a fresh burst of star formation, so the donor in the high mass is a very large star, low metallicity, so it is sensible that we have the high luminosity tail of these sources. The cutoff is probably seen it's difficult to define, and we want to see if the ULXs agree with this cutoff or not. Theoretically possible that the largest black hole are around 90 solar masses in 2004. There are more recent papers by Speer and Mappelli that goes up also to 120 solar masses black holes. We don't know them in our galaxy, but they might be frequent in other galaxies. I have constructed the luminosity function of 2 galaxies. One is the Cartwheel, and the other is not a ring galaxy, it's NGC 2276. If one remembers, it was the first group that was detected, the group of NGC 23,000, the first group detected in X-rays. Comparing them with the Grimm et al. Luminosity function rescaled to a proper star formation rate, we see that the luminosity function that we derive are not much different from the one of high-mass X-ray binaries. Other papers like the Mineo et al. Have done the same work, and so again they find a cutoff around 10 to the 40. In the Cartwheel, there is only one source which is above this cutoff line. So with all the sources in the rings of these 7 galaxies, I have more than 60 sources, 50 of them are ULXs, and so I can construct a more numerous X-ray luminosity function. And again, if I plot the Grimm et al., these 2 green lines are 2 different models of the Grimm et al. Luminosity function, a different normalization, one with 30 solar masses, the other with 50 solar masses in total. The sum of the star formation rate of our 7 galaxies is around 33 solar masses. I will talk about the star formation rate a bit more later. It's very, very difficult to have a good measure of star formation rate. So these numbers are not very unknown, but not with large error bars. The red line, instead, is the luminosity function derived by Schwartz et al. With another catalog of ULXs derived with Chandra. They have 100 sources, and the star formation, the effective star formation rate that they compute is around 50 solar masses. So we are about in the same range of total star formation rate. And we see that the Schwartz et al. Slope is a bit steeper than the one that we have found. there are two sources above the cutoff line. As you can see, the statistic is not high, so we cannot put a compelling result that the two are different. These are the individual luminosity function, and you see that some sources like the Cartwheel have a lot of bright sources. ARP 148 has only two sources, but this is just because of the high upper limit of detection that I was mentioning before. So we can compare this sample with the result of correlation between the number of ULXs and the star formation rate, and as was done before, we have some estimate of the age of the impact for a few of them, and it goes from 30 to 400 mega-years, so all the stars are young if they are made after this impact, and they might be much younger than these ages. And so the ring is linked to the current star formation episode. Michela had done work with 66 late-type galaxies and constructed the ratio between the correlation between the number of ULXs in galaxy and the star formation rate. And so we have added these new points to her graph, and you can see that they tend to be at the highest level of the distribution, but are not inconsistent with the distribution already found. This is ARP 148, which it's a bit lower, but I told you this is most probably a lower limit on the number of ULXs. What about the dependence on metallicity? I already told you that there is a sort of a trend of star formation rate, of the number of ULXs normalized by the star formation rate with metallicity. There was a recent finding that metal-poor X-ray binaries are more luminous than metal-rich pairs, and so this might enhance the luminosity of the sources and make them more in the ULXs area. As I was telling, the star formation rate has large error, but the metallicity is even more uncertain. And if we put the dots in this trend, you see that the trend is not very strong, so it's very difficult to confirm it. We see that they tend to be, again, in the higher part of the diagram, but now we have large uncertainties, and for instance, this object, which is NGC 922, it's plotted at metallicity 1, which is the solar metallicity that has, the only metallicity that has been published for this source, but this is a nuclear metallicity. While we have some spectra of the outer part, which have not been published yet, which tell us that the metallicity of the ring is much lower than the nuclear metallicity. And so if we put this at a lower metallicity, it goes again in the middle of this distribution. At some point, we were asking ourselves if this was the fact that these sources are so bright is because they are bright and famous. So we have picked the brightest object just because they are so apparent in the sky because of these large and evident rings. And so we try to make a statistical sample of ring galaxies. So we've gone to the ARP-Amador sample, which collects all ring galaxies, and we have selected all the ring galaxies that are defined collisional ring galaxy, in the sense that they have a companion at the same redshift, which might be the bullet, and have this ring of star formation that is apparent in the optical morphology. And we have selected all the objects that are nearby, so at redshift smaller than 0.02, which correspond to a distance of around 80 megaparsec. The Alpen-Mador was done in the south, so we have a cut in declination, which is south of minus 22 degrees for completeness. There are only 12 sources that have all these properties, and 10 of them were observed with XMM or Chandra. One of them is an AGN and also has a different redshift. I will show it afterwards than the one that was listed in the Alpen-Mador catalog. One does not have any useful data, so we have 8 galaxies in the end. We had predicted the number of sources that we were expecting from this. So basically, the star formation rate of these galaxies based on their blue luminosity and compare it with the Cartwheel. And we were expecting a large number of X-ray sources. These are the finders of these sources. You can see that some of them have nice rings, some are more complex in appearance. For some of them you have to go, these are with the Palomar Sky Survey, you have to go deeper to see better the appearance of the ring. This is the object that has been found to be an AGN. This is not a collisional ring, but is an interesting object. The luminosity is 10 to the 41, also because, as I told you, the redshift is higher than what was listed in the Alpen-Mador catalog. And it has this large extent, it has a very strong point source and a very large extent in the X-rays, which correspond to this structure that has been interpreted as the ring. But we believe that it might be a central dominant galaxy in a group, or because otherwise we would not expect this strange shape in the optical morphology. The galaxies that we have observed, I'll show you just a couple with the X-ray data. This is XMM data. Even if it is XMM, so the resolution is not quite high, I believe that this source is not located at the center of one of the two galaxies, so it's not the nucleus, and so it's most probably a ULXs. This is a bright star which makes a mess in the field, so the region, sources in this region, in this direction, might be spurious, but luckily ours is not in the direction of the pixel of the CCD. This is another clear if it is close to the nucleus or not, and so it's very uncertain, the definition. But in the end, we have only 7 sources, and 2 are uncertain with in these 8 galaxies. We have detected 2 nuclei, so it's about the same fraction, about a fourth, a third of the ring galaxies have a nucleus that is active in X-rays. There is some excess, so besides these point sources that are detected, that there is some diffuse emission. So this might be either gas, hot gas that emit in X-rays, or some other not resolved point sources. So we were puzzled, and we are starting to find other ways of looking at or defining the star formation rate for this object to compare. We have found that the blue luminosity is not a good tracer for this object. The star formation rates that are published are very, very difficult to use because the total we see from IRAS is about 5 solar masses per year, and for 4 of these 8 galaxies. But they might be contaminated by the nucleus, because with IRAS we cannot discriminate the contribution from the nucleus. If you use GALEX, we have 6 galaxies, and the total star formation rate is 1.1, so we get very different number. And for instance, if you take one galaxy, 1434, it has 0.7 from Galax and 3 from Iris. So it's very difficult to know which value to use. So we are working now with our H-alpha image. We have H-alpha image for 6 galaxies, and we are in the process of reducing this data. And these are the orientation is different than the previous images, but you can see that all of them have some H-alpha emission. Not all of them show well the ring. This does. This ring is clearly seen, but I'm not truly convinced that it is a collisional ring by its shape. So even if this is a work in progress, we can start to compare with some results. And if we use the number of ULXs compared with the star formation rate derived from H-alpha, we see that we have an excess with current normalization. So this, even if it is smaller than what we thought, might still be an indication that this object tend to have a higher number of ULXs for the star formation rate. Even if they are, this can be considered as a sort of a complete sample, if it is not formally complete, but is a random sample. And so we can compare this with the sample of the brightest sources. And again, the total luminosity function is higher than what expected for the star formation rate. So this could imply that the rings have a higher luminosity in X-rays than the other spiral galaxies that have ULXs. But this is not a final result because we did not do yet correction for the extinction, and this might change a little bit the star formation rate that we derive for these sources. If we take the 5 sources, even including the 2 candidate sources, and we construct the luminosity function, I cannot correct this for incompleteness as I've done before, because this is a mix of sources from Chandra and XMM, so it is not a real good sample of to make a luminosity function. And I could correct with Chandra because there are some studies that can derive the number of sources that you lose because of the presence of a higher background in the galaxies, and so you tend to lose sources at the faint fluxes. But you can think that this flattening here is due to incompleteness, and you can think that the real luminosity function is a bit steeper than this. In any case, I've plotted the Grimetal function with the 3 solar masses, which is roughly 3.5 is what we have found for this sample. And we see that they are not much farther away from this. So it is reasonable to think that also these sources have a number of ULXs which is consistent with the star formation rate. So the question remains to be answered, are these sources intermediate mass black hole or are they neutron stars, and how to find out. And so I've seen recently a paper by Grzegorz Wiktorowicz, which have done a very nice prediction of the number of ULXs based on first principles. So he has taken a population synthesis model, has taken some evolution, and has counted how many of these objects become neutron star or black holes. And he produces some numbers, and I can compare with the luminosity function of the cartwheel, which is plotted here. And there are a lot of things here, but the basic result is that after 1 gigayear, this is the number of neutron star if there is only a burst of sources, but they are black hole if the star formation is constant. And in 5 gigayears, the number of black holes goes away. So we can see black holes with a fresh burst of star formation. And now I intend to work, this is just a rough calculation. And I'm sorry, this is the number of black holes that you expect at different luminosities, while this is the number of neutron stars that you expect. So the number of black holes is that he finds is much larger than the number of neutron stars. So now I intend to use to work better to derive the age of this star formation episode in the cartwheel, and to have better metallicities, so that to have a better comparison with his models that he's also refining at this time. So we might have in a few months maybe a better answer on the distribution of sources in these galaxies, to see if they are actually, if they're expected to be on statistical grounds, more likely neutron stars or black holes. And so, just to conclude, I cannot say, I can just say that ULXs are a very interesting population. You start to look for something and then you end up finding something completely different. In the 7 ring galaxies that we will publish soon, we have more than 60 sources, of which 50 are ULXs. And this is just considering the ring of the ring galaxies. And this is comparable with the 100 sources in 127 galaxies that Schwartz et al. Have found. So ring galaxies really have a large number of ULXs per galaxy. And the luminosity function is consistent with previous result, so with both the Schwartz et al. Luminosity function and the Grimm et al., which is not distinguishable on statistical ground, but we tend to see brighter sources and with a larger number, and also with respect to the star formation and the metallicity of these galaxies. And we, especially at high luminosity, we expect them to be most probably black holes, but the two brightest sources in the luminosity function are the most interesting object, because one is the brightest object in the cartwheel that we had already proposed to be either a 100 solar masses black hole or a very bright supernova, and we would need to observe it again in X-rays to see if it has changed the luminosity or if it is still at the same luminosity as before, and this would discriminate easily the two models. Not easily. But we've tried to get some Chandra data again, and we have not succeeded yet, and so we will try again next year, and maybe we have also an answer on these two bright sources in our luminosity function. Thank you.
Thank you very much, Anna.
Sta andando bene anche la voce.
This very nice overview of the property of ULXs, which continue to serve surprises of different kinds and becoming more and more interesting as time goes on. Thank you for this, presentation that you work at specifically. Prego.
I'm losing my voice.
Me too.
Okay. So you haven't mentioned the class, group, subgroup of these ULXs that people often call the ULXs, the ultra-luminous sources. So they are extremely soft, but some of them are trends, and some of them are also states in which they overlap with your ULXs, they become hard. And they're probably a mixed bag. I'm interested in the possibilities that some of them are actually quite dwarf binaries, because we now know in Magellanic clouds and all class of the solid seeds of these stars with quite dwarf companions that are very X-ray luminous. But some of them, the local universe, 2 of them, have been proven to be stellar mass 20 solar masses, black holes, and so on, and one and M81. And so I don't think that these are so different from your harder galaxies. And it looks like strong proof that they are not, that they may be, I mean, the black holes, it's a mixed bag of objects, but the black holes among them may be not intermediate mass black holes, but rather are massive stellar mass black holes. Because we see too, we know that they exceed the luminosity of 10
Yeah, I have not specifically worked with those sources, so I did not say anything because I have not done anything specific with those. The fact that they have a different X-ray spectrum might tell us that they have something different. I don't know exactly, because there is a spread in spectral shape also for the classical ULXs, but they tend to be much harder than the super soft sources. So there might be some different aspect.
That these sources which have much softer spectra, like M101, ULX1, according to the idea,
According to
the idea that there might be accreting black holes because
it's not an idea, they measure the masses too, they have masses.
yeah, but I mean, for
They
the
know
other
it.
ones, right? For the other ones, according to the, if they contain black holes and they are accreting above the Eddington limit, then what you see in this case probably more ion-conditioned system where you see the wind coming from the equation, sort of television. Then you have a sort of
You say if, but I'm afraid there is not much if. I'm afraid it's a fact.
for M101,
And then for the meeting one, also there is strong proof.
well, there are doubts, I mean, there are targets with measuring the black hole mass that you may be aware of. It's just based on 8 spectroscopic points and, some follow-up would really be desirable to really be, to put these spectrum on the safe side.
Don't believe them.
No, I believe it, but I mean, it should be, it is uncertain, okay? But I mean, the indication is that that's specifically sort of fine component of the core, which might be of low mass, but even larger, that's a lower limit from the not another strip. But for the other ones, the idea that they contain that for the other soft is thus being by knowledge.
Roberto.
Sure, would be confirmation either from the transnational or from the science.
One comment, one question. The comment is you speak about collision ring. Actually, we don't encounter, I mean, they got collision by a special class of collisions. On the other side, you have other collisional rings, which are the normal rings, perhaps in early galaxies. Collision in the sense that two galaxies pass nearby each other, and collisionally they create a instability in the disk.
These are gravitational ring more than collision ring.
Gravitational at all. They are created by instabilities in the disk, created by companions which fly by. So this is the question: why you restricted your research on head-on encounters? I mean, for instance, 1291, as we said, been studied recently by Pepe Fabiano and Don Wu, the possible name for me, and they found that ULX, large population of ULX, right? I mean, why you restrict to this kind of specific?
This is an encounter that should have the highest energy involved, and so the highest probability of making new, a highest.
So
triggering a high population of new stars.
But in spite of that, also in
Yeah, but I'm not saying that the other encounters do not produce. In fact, in 2276, the galaxy, I don't know if you know, remember the object, there is a huge elliptical in the middle, and this is a spiral that is passing by. It's quite distant from the elliptical, but still the morphology is quite altered, and there is a very large number of ULXs. So there are many different situations in which you make.
This my question is just to include the statistics of this object to understand knowledge.
Yeah, but we wanted to select this because in this case also you have the ring, which is the locus of recent star formation, and you end up minimizing the effect of interlopers, in which when you have a large number of sources and the large size of the galaxy, many of the sources might be not associated to the galaxy. And so this is another reason to just choose those and not other galaxies. But when we are finished with this, we can go on with others.
So it's probably much clearer association in geometry with the age, right?
And also the, yeah, and also
that you have in this case, I mean, of these very nice, beautiful rings. But of course, there are several other situations which you could explore in the future probably. But
yeah.
These are probably the best cases you might consider at the beginning. And you know very well where the location of star formation rate as a function of the age of the system.
It's elliptical.
Yeah.
Yeah.
See, if there are no other questions, we thank Anna again. Thank you.
Se vuoi farlo firmare che sia certificato, bene, ma se no lo firma e cosa, poi dopo glielo dai alla tua segretaria lì, ci pensano loro, lo scansionano, lo mandano, perché siccome a Brera fate ancora cartacea sta roba.
Allora,
Me l'hanno spiegato da me, no, non è
elettronica.
No, fai tutto cartaceo. Brera non fa elettronico.
Non è vero, stiamo incominciando a farlo anche
Però
noi.
quello lì delle missioni per i seminari mi ha detto la mia donna della...
questo?
No, lo spendiamo di là, di là. Me l'ha detto la mia donna dell'amministrazione, siamo ancora cartacei.
Io questa missione ho fatto la richiesta online, ma secondo me l'ho fatta sbagliata, perché probabilmente lo faremo cartaceo.
Fai quel pezzo lì di carta e poi chiedi il rimborso alla tua amministrazione.
Sì, quello lo
poi
so.
Poi ci pensano
quello lo so.
loro. Ah, ma allora, ma tu avresti tempo